Good afternoon. I am Pranay Sharma. I've been teaching in S.MONK for past 5 years. I teach CM1 and CS1, and today we are going to start with our CS1 course. Now CS1 is nothing but Core Statistics 1, and we are going to study the statistical analysis, analytical tools that we require, that we are going to study in this subject. Okay. So our course contains 15 chapters. Okay. We are going to go from very basics of statistics to all of the analytical tools. So basically first six topics are our basics, and then from 7 to 15 these are all analytical tools. Okay, these are analytical tools that we are going to use not only in this subject but throughout statistics. These are the analytical tools that will be required throughout the statistics that you are going to study in actuarial science. Okay, so very important. Now, other than that, we are going to start with basic chapters, 3 basic chapters that you are supposed to already know, but we are not going to assume that. We are going to study 3 basic chapters. First is probability. Second, summary of data. And third is going to be random variable. These are the basic chapters that we are going to study before we start our actual course. So today we are going to start with probability. So that is our basic chapter. I'll write it as B1, basic chapter 1, probability. This is what we are going to start with. Now before we go on to studying our chapter, we require a scientific calculator. Okay, so if you are giving examination from IAI, that is the Indian Institute, then the calculator that you would require is Casio FX 82ES Plus. Now if you are going to give the examination from IFOA, that is the UK Institute, then the calculator that we use is Casio FX 991 ES Plus. Now there is no restriction of calculator in IFOA Institute, that's the UK Institute, but this is the recommended calculator by me because all the functions or everything that we'll need to do is already present in this. Although everything that we are going to need the calculator for is also present in this 82ES Plus, but there are a few functions that are handy in 991 that are not present in 82ES Plus. That does not mean you cannot use 82. Every calculation that we are supposed to do in the calculator can be done with this 82ES Plus. But in 991, there are a few things that we can do more. That's it. Okay. So these are the calculators that you are going to use. Let me just show you how do they look. This is the 82ES Plus. Okay. So first of all, this one calculator is the old version calculator. This is the new version. This is how the new version looks. For function wise, there is no difference between both of these calculators. Mostly the look has changed. I did not find any changes in the actual functionality of these calculators. So even if you have the old calculator, that is fine. And even if you buy the new one, that is fine. This is edition 1, this is edition 2. So whichever you get, you can buy it. And similarly, the 991 looks exactly the same, just the color difference. So you can see this is the old calculator. Okay, just the color difference from that 82ES plus, and this is the new calculator. Okay, so slightly color difference, nothing much. Okay. So we are going to use scientific calculators. Now in this, you can see the layout is exactly same, so it does not matter which calculator you buy, you will get the same layout of buttons. Now, throughout our course, we are going to study how to use the scientific calculator. So even if you have never used the scientific calculator, that is fine. We are going to learn it here. Okay. So I am using an app. Okay, I don't remember the name of the app, but in Android or in iOS, you can just search in your app store for scientific calculator and you'll get a lot of options. You should choose only the option which has navigation keys in between. So you can see these 4 arrows, right, left and up and down. So any calculator with these 4 arrows would be fine. But I would suggest that you buy the physical calculator as soon as possible and use that, because the more practice you do on the physical calculator, the easier it will be for you to study and later on use, or the faster you will get and you will make less mistakes. Okay, so have the physical calculator, but by the time you don't have it ready, you can download an app. Problem is the apps have a lot of ads and stuff that might be very annoying. So have the physical calculator and keep that with you everywhere you go. Okay. Now I'll just give you a basic rundown on how the calculator works. So these are our normal buttons. You can see multiplication, division, addition, subtraction, equal to. These are our normal calculator layout. Okay. Now these are the special keys. These are the scientific calculator difference from the normal calculator. So most of them you will be easy to recognize. This is the root. This is division. This is square. This is raised to any other power. You can see log. Log is log to the base 10. Ln is log to the base e. Okay. Hyper, sine, cos, tan, these are all trigonometric functions. We are not going to use trigonometry, so these are of no use to us. Okay. Here you have some integration. Here you have raised to minus 1. This is used when you have to use log to base any other than 10 and e. Right. So these are the basic keys. Now we have some more functions that we can use by using this shift or alpha button. So you can see anything written above a key in yellow can be accessed by using this shift button. By using shift button. And then anything written in purple here can be accessed by using this alpha button. So these will be very important for us. There are many modes that we are going to go through as we go along. For that we have this, but right now I will just take an example and show you how you can make an equation in your calculator. So we all know quadratic equation. Let's say I'll make a quadratic equation. We know to solve this quadratic equation, we say we have minus b plus minus under root of b square minus 4ac upon 2a. This is how we make the roots of a quadratic equation. So accordingly I will have minus 6 plus minus under root 6 square minus 4 into 3 into 2, 2 into 3. This is the equation. I can make this equation directly in our calculator. I'll show you how. So what I'll do is, first I want the fraction. This is the fraction button. Press that and you can see the navigation. this arrow, this or whatever you want to call it, cursor is on the numerator. So I can type whatever I want to in the numerator. So -6. I will do the minus first and then later on we'll do the plus. So I cannot do plus minus both together. And I want root. This is the root. So root. Now 6 square. So 6, and you can see the square button here. If I wanted any other power, I would use this and substitute the power. So right now 6 square minus 4 into 3 into 2. Now you can see as I was typing the equation, it was always under root. So you can see the root is extending. That is because we are writing inside the root. If I want to go outside, I will press this navigation keys. Okay. So if I press this side arrow key, I will get out of this root. Okay. I want to go down, so I will press the down arrow key afterwards. So I will press the side arrow key. It will come out of the root. If I type anything, you can see it is not, now root is not extending, right? Because I am outside the root. And if I press the down arrow key, I am going to go down. You can see the cursor is now down here, and I will have 2 into 3. So this is one root. Now many times you will find that your answer is shown in fraction, and if you want it in decimal, this is the button, SD button. You can see above del. That's the button that you will press to convert your answers from fraction to decimal or decimal to fraction. Now I want the second root. I want the plus here. So what I can do is I can edit this equation. If I press AC, I will have nothing here. Do not press the on button because your calculator stores the 10 past equations that you have used. So if you use the navigation key, this up arrow key, okay, I get my previous equation. If I go up, these are the other equations that I have used before. If I press on key, then I will lose all of these equations. So again, when I am in blank, if I press up arrow key, it gives me the previous equation. Now, if I want to edit this equation, I will press the side arrow key, and you can see that I have now edit option here. You can see the cursor. Now I can delete this minus and add a plus. That becomes the second root. So this is how we can use the scientific calculator. As we go along, I'm going to teach you throughout, so you don't have to worry about it. Anything that we'll require, I'll teach you how to use in your scientific calculator. So do buy the calculator as soon as possible. Both of these have almost the same layout, slightly different layout. Okay, maybe one key or the other here and there are different in these two, but you will not have any problem in understanding using this layout. Now make sure that you are buying ES version only. There is an MS version. Do not buy the MS version. There are certain functions that we require that are not present in MS version, okay, but are only in ES version. So make sure that you are buying the ES version of the calculator, not the MS version. Let's go to the basic one chapter, that is our probability. First of all, what's a probability? I would like us to have an interactive session every time. So at any time you can answer or ask question by writing in chat, or you can unmute yourself and talk to us. Okay. So when I say probability, what does the first thing comes into your mind? Hmm? Anyone? Likelihood. So Vedant is saying likelihood. Devanshi is saying chances. Both are correct. Okay. Uh, Advo is also saying chances of happening of an event. Yes, perfect. So when I say probability, it is nothing but chances or how likely is something to happen. Likelihood also means the same thing. What are the chances? Okay, and the chances means probability. So if we figure out what are the chances of something happening, we call that as the probability. So how do we figure that out? We say that probability of any event is going to be nothing but the desired outcomes upon the total outcomes. So if I run some experiments, do the same thing again and again, how likely is something to happen? That tells us the probability. So that is nothing but how many times our desired outcomes happened upon how many, out of how many times the total event was run for. So that becomes nothing but the probability of an event. Now in probabilities, we can write it in terms of sets. Okay, so we say probability of A can be written as number of elements in A upon number of elements in our universal set. So we'll go through sets quickly. I hope everybody has studied sets. So we'll go through sets very quickly. So first of all, sets are nothing but collection of similar events or similar things. So whenever I am saying a set has A, B, C, D in it, so that would be nothing but collection of first four letters of English alphabet. That would be A, B, C, D. Correct. So it is collection of similar things. There is something common between them, and that becomes the main difference between just a collection and a set. Okay, so it's a collection of similar things. Okay, so let's say I have set A that has, let's say, A, B, C, D, and let's say set B, I have C, D, E, F. Now a set can be written with capital letters. Okay, and the elements in it are represented by small letters and separated by commas. We write them in the curly brackets. That is how we define a set. Now whenever we are talking about a set, we say that the events inside it or the elements inside it are unique to each other. So that means this A and B are different from each other, the C and D are different from each other. And we say in the whole universal set that contains everything, we are going to always say that there exists one item only once. That just means this D that is in set A as well as in set B must be the same D. Okay, because one item exists only once in the whole universe. That is what our assumption is. So these D or this C are the same C and D in the both sets. So there is something common between them, between A and B there is something common between, we call that as intersection. So we say A intersection B is going to be C comma D. These are the two elements that are common between A and B. So that is nothing but intersection. Then we have union. Union means together. Or you can say either or. Okay, you can, okay, instead of together, just write either or. So in union, we are going to say an element that is in either A or in B. We write it as A union. Okay, it's not actually U, we call it as cup, and this intersection term is called as cap. So A union B, it will contain all the elements but only once. Okay. So C and D were common, so they'll come only once. That becomes our union. Then we have complement. Complement means everything other than. We say complement, the simple term complement just means it has something that completes this set. Okay. So complement, if I write A complement, there are many ways of writing. People write AC, or they write A bar, or they write A minus, no, not minus one. I think AT also, I am not sure. I don't remember. So anyways, we'll write AC. I think these are complements. Okay, we'll write AC. Complement, we'll say it is everything other than A. Okay, so we'll take all the universal set, and in that, if we subtract everything that is contained in A, that becomes A complement. I think A complement is written just A dash, not minus. Okay. So complement just means everything other than that element A. Now we are more interested in the number of elements. So if I say number of elements here, the example number of elements in A is 4 and number of elements in B is also 4. Number of elements in A intersection B is 2 and number of elements in A union B is 6. We say that number of elements in A union B is nothing but number of elements in A plus number of elements in B minus number of elements in A intersection B. The formula, and this can be explained very easily using Venn diagrams. Venn diagrams are just diagrams which are used to represent the sets. In a Venn diagram, we make a square, that is the universe. So universal set, that is X, it is everything. Universal set can be written as U, X, S, whatever you want it. Okay, I write it as X, you can write whatever you want. Then the sets are represented with circles. So here we have two sets, so I will make two circles. Let me make it from different colors. So the area under the circle is nothing but the elements. So area under the circle represents the elements. So this part we'll call it as only A. This is contained only in A. This part is only B. This is contained only in B. But this part is the intersection part that is contained in both A and B. So when I'm counting the number of elements in A, that will be this complete region, and I'm counting the elements in B, that would be this complete region. I'm counting the intersection 2 times, and that is why we'll have to subtract it once. Right? So number of elements in A plus number of elements in B minus number of elements in A intersection B. Okay. Now we can have 3 elements as well, A, B and C, 3 sets as well, A, B and C. So if I want to find A union, B union, okay, before we go to that, I want to write this formula in one more term. So now I can write this as number of elements in only A plus number of elements in only B, and then plus number of elements in A intersection B. Because I can add up this only A, I can add up this only B, and then I can add up this intersection part. If I add up all these 3 parts, I am going to get again the union that makes everything. So how do we represent this only A? This only A, how do we represent that? Now I can say this is nothing but number of elements in A but not elements in B. So B complement. So whenever we are converting a statement into sets, okay, mathematics, we say intersection can be written as and, or it can be written as but. These are all the same thing. Similarly, when I am union, I am using union, I will say it is nothing but or, either or. So I'll say any element that is in A but is not in B would be represented as only A element. So that is A but not B. Similarly, here I can say it is number of elements in not A but B. Element that is in not in A but is in B, that is only B. And then A intersection B. Okay. This is how you can use complements. Now let's say you have 3 elements. three sets A, B and C. A, B and C. First of all, if I want the union, let's say it is number of elements in A plus number of elements in B plus number of elements in C. Then we'll subtract. See, when I'm adding up A, B and C, the common region, that is A intersection B, A intersection C and B intersection C, has been added twice. I need to remove that once. So A intersection B I'll subtract, B intersection C and A intersection C I'll subtract. But then when we look at this triple intersection region, that was added 3 times when we added ABC. That was subtracted 3 times when we subtracted the intersection. So I will have to add that once more. A intersection B intersection C. I will have to add that. So that is how we write the equation for A union B union C. Now I can also label this, let's say, only A region as A. This, let's say, is B. This is C, D, E, F, G. Now if I add up all of these individual regions, I am going to get again A union B union C. So that A region, I can say it is only A. B region is only B. C is only C. Similarly, D is A and B but not C. So I can say it is A and B and not C. So I'll write it as A complement. Similarly, the E region is B and C, or I'll just write it not A and B and C. Similarly, the F region is A and C but not B, so not B and C. And then we have triple intersections. So similarly, only A can be written any element in A but not in B but not in C, plus only B can be written as not A but B but not C. Only C can be written as not A, not B and C. Then A and B but not C would be A intersection B, not C, then not A, B intersection C, then A not B and C, and then we have the triple intersection. So this is how you can write each one of those regions. Represent them with intersections. Okay. Now, other than that, a few things. If you want to make a formula of union with 4 sets, so if I have A union, B union, C union, D. If I have 4 sets, what happens is first I will individually see what happens is we add up individually each one of them. So I'll add up, let's say number of, I just put I. Okay, individually I will just add them up. Then I will subtract single intersection. I'll write it as I intersection J. We will add up single intersection for each one of them. So that would be A intersection B, B intersection C, C intersection D, and D intersection A intersection C, B intersection D. All the combinations. All the combination taken 2 at a time, I will subtract that. Then I will add the triple intersections. So I'll say I intersection J intersection K. So that would be ABC, BCD, ABD, and ACD. You will add them up, and then you will subtract the intersection for all 4 of them. Intersection between all 4 of them. So this is how it works. For 5 also you will do the same thing. Add up individual, then subtract single intersection, then add up triple intersection, then subtract 4 intersection, then add up the 5 intersection. So alternatively you do plus minus and increase 1 intersections. That is how the general formula works. We don't really use 4 unions, 4 intersections and stuff, because we understand the concept. We don't need to use it in our course. Okay, so we are going to see 2 sets or 3 sets. That is very common, but 4 sets we don't really see them. Then simply, if you have A union B complement, that is same as A complement intersection B complement. A intersection B complement is A complement union B complement. These are the few things that we need to understand about sets before we go to probability. Now probability of an event A. Okay, so event are very similar to sets, where the outcome of the event is going to be nothing but the elements of the set. So probability of A would be number of elements in A upon number of elements in X, or we'll call it as number of outcomes in A upon number of outcomes in universal set, or the total outcomes. That becomes nothing but the probability of A. Now what happens is all the formulas that we made for number of elements can be easily translated to probability by dividing each, both left hand side and right hand side with number of elements in universal set. If I divide by this, what I get is, I get probability of A union B. Similarly, here I'll have probability, here I'll have probability, here I'll have probability. So formula remains same. Here also we will have probability, probability, probability. Instead of n, we have probability for everything, for this as well, for this as well. Everywhere you had n, now becomes p. So all the concepts that you have learned in sets can be directly translated into probability. Let me take an example. So from a deck of 52 cards, one card is randomly chosen. Find the probability that it is a club. So if I assume being club is event A, I'll say probability of A. So how do we figure that out? We'll say in total I have 13 clubs out of 52 upon total 52. So I have 13 choices for a club out of 52 total choices. 13 by 52, you can simplify it, but I'll leave it 13 by 52. For the second, that it is a 7. So if I assume it to be B, it's a probability of B. It's a total number of 7s in the deck is 4 out of 52. Again, I'm leaving it like this. You can simplify it. I'm leaving it like this. A third, it is a 7 of clubs. Now, out of whole 52 cards, there is only one card that is going to be 7 of clubs. And we'll say it is A intersection B because it is 7 as well as a club. It becomes A intersection B. And we have only one card out of the whole of 52, that is 7 and a club. Fourth, it is a 7 or a club. When I'm saying 7 or a club, I am saying it is A union B, because I can have a 7 that is not a club as well. I can have 7 of hearts, that will also be part of it. I can have 7 of whatever, anything else. I can have all the clubs. Now, I have 13 clubs and I have 4 sevens, but one of them is the same card. So in a way, I have only 16 cards, that could be a 7 or a club out of 52 becomes A union B. There's another way of writing A union B. That would be probability of A plus probability of B minus probability of A intersection B. And you can see you have 16 by 52. That is why I did not change the, or I did not find the lowest fraction. I just leave it as denominator 52. It's just easier for us to add and subtract. So you can see probability would work exactly the same way as the sets would. Any problem here? Okay. Now, uh, when we are finding probabilities, we are talking about an event. So let's talk about different kinds of events. So first, we are talking about mutually exclusive events. So mutually exclusive events are events when two events do not have any outcomes in common. If they do not have any outcomes in common, then they are mutually exclusive. Okay. So mutually exclusive, no events in no elements in common. That means probability of A intersection B is always going to be 0. Okay. So no elements or no outcomes in common, then we'll call them as mutually exclusive events. Then we have mutually exhaustive events. So mutually exhaustive events. So we say when two events together share all possible outcomes amongst themselves. So when two events have complete all of the outcomes together, then they are called as mutually exhaustive. That means A union B should have all the outcomes. So probability will just become 1. Now we know that probability always stays between 0 and 1, because the minimum would be there is nothing, no desired outcome, so 0, and the maximum is going to be it contains everything, desired outcomes are everything, that will be 1. Probability becomes 1. So in this example, can you tell me A and B, that is selecting a club or selecting a 7? Can you tell me, are they mutually exclusive? No, they are not mutually exclusive because they have something in common. Are they exhaustive? So no, because together they do not make up the complete universal set. Okay, we still have some elements that are not part of A or part of B. So these were neither mutually exclusive nor mutually exhaustive. Okay. So if I want to give you an example of mutually exclusive events, so the suits, all the suits of the deck, the hearts and the clubs and spades and diamonds, whatever we call them, right? So each one of them do not have anything in common between each other, so they are all mutually exclusive of each other. Similarly, together all 4 make up the complete deck of 52 cards. So together all 4 are going to be mutually exhaustive events. So 4 of them coming together are mutually exclusive, and together they make up the whole complete set. That means 4 of them are exhaustive to each other, mutually exhaustive. So it's not necessarily that we can have only 2 events, we can have more than 2 events also. Next, independent events. We say if occurrence or non-occurrence of the first event does not affect the occurrence or the non-occurrence of the second event, then they are called as independent events. So basically, existence or non-existence of the first event is not affecting the existence or the non-existence of the second event. Or you might call whether the first event happened or not is not affecting the probability of the second event happening or not. Then they are independent events. Mathematically, we represent it as we say if A and B are independent, then probability of A intersection B is equal to probability of A into probability of B. That means both of them occurring together. Okay, probability of both of them occurring together is same as A occurring and B occurring, because they are not affecting each other. Because they are independent of each other. That is why they are not affecting each other. That is why them happening together is just a coincidence. It is same as probability that A happened into probability that B happened. Or we can have probability of A not occurring and B occurring same as probability of A not occurring into probability of B occurring, or both not occurring or A occurring and B not occurring. Just happens individually because they are independent of each other. So all four are going to be true. You can convert one into the other. Now can you tell me that the example where we took above, where let's say A was picking a club and B was picking a 7. Can you tell me whether A and B are independent of each other or not?
They are independent.
They are independent.
They aren't. They are not.
Okay, they are not independent. Okay. Anybody else? If we look at the probabilities, probability of A into probability of B, are you getting it as equal to probability of A intersection B?
No.
Yes, it is. 13 into 4 is 52. One of the 52 will cancel out and 152 will be left. So 1 by 52. Right? 13 by 52 into 4 by 52 is actually equal to 1 by 52. Right? So are A and B independent events? So then they should be independent events. Right? But they are neither independent nor they are dependent. The reason being they are not individual events. They are actually outcome of one event, and that one event is picking a card. The one event is that we are picking a card, one card. And they are nothing but the outcomes of that event. Okay, picking a club and picking a 7 are nothing but outcomes of picking one card. Now they are events in themselves as well, but one of the properties of a set is that a set can be subset of another set. Similarly, an event can be an outcome of another event as well. So this picking a club is also an event, but it is outcome of this event, that is picking a card. This B, that is picking a 7, is also an event, but it is an outcome of this event, that is picking a card. So actually, picking a card is the event that is happening here. Picking a club or picking a 7 was an outcome of those events. So if I have only one event, how can it be independent or dependent to itself? So it cannot be, right? It cannot be dependent or independent. Now let's say that I change the scenario here. I say picking two cards. Now I have two events, picking first card and picking second card. Now if I say what is the probability, or in the first card I am picking a club, in the second card I am picking a 7. Now can we have them as dependent or independent? Now tell me whether they are independent or they are dependent. Anyone? Now I am saying that we are picking two cards. First is a club, then second is a 7. Can you tell me whether they are independent or whether they are dependent? Again, guess, does not matter. See, even if you are wrong, it does not matter. Okay, you have just two choices. So 50% of the times you are going to be correct, 50% of the times you are going to be wrong, and it does not really matter, because here we are here to learn. There is a saying that if you are not wrong, that means you are not learning anything. Because if you are always right, what does that mean? You don't need to learn anything new. You have all the knowledge. So if you are always right, that means you don't have anything else to learn. We are here to learn, so we'll definitely be wrong sometimes. And only then we'll be learning anything new, right? So don't worry of being wrong. We should always participate. We should always think of an answer. See, if I am only teaching you everything and that is why you're learning, that is not how the learning works. I would like your opinion. I would like your thought process to come out first, and then I will say whether your thought process was in the correct direction or it's supposed to move in some other direction. Correct? So I would like you to think before I give you the answer of anything, or before I tell you anything. So now tell me whether they are going to be independent or dependent. I hope everybody understands. Now we are picking two cards and we are finding probability. For in first card we are going to say picking a club. In the second card we are going to say it's picking a 7. So whether they are going to be independent or whether they are going to be dependent. So we got one answer from Vedant that they are. Is it independent? He is also asking question. He is not even answering. So it's fine. Others, I would like you to also either type or just you can unmute yourself and talk. Okay, the class is always going to be like we are moving in a car. Okay, and now you have two lanes. One is going right, one is going left. If you don't choose, you will, crash. Choose. That's the point here. Okay, and let's not crash. Right. So there are some dependents, there are some independents. I'll tell you that neither of you are correct nor wrong. I, misled you when I said you have only two options. You don't have only two options. Actually, we cannot decide whether we are independent or dependent. These two events are dependent or independent, that because I have not given you the complete information. There's one more thing that we need to know before we can decide whether these are independent or dependent events. That what is happening in between picking these two cards. Now see, when I pick the first card, I see it. Then if I replace the card back in deck, reshuffle it, then these will be independent. If I replace the card. But if I do not replace the card, first card, then these two events will be dependent on each other. Okay. So it matters whether you are replacing the first card or not. Why does it matter? Okay. Now forget about these two events. Let's assume we are talking about picking a let's say picking a ace. Okay. So now let's say event C is picking a ace. So in the first card, if I see the card and then I replace it back into the deck, what happens is, in the first probability that C1, I get an ace in the first card, is going to be 4 by 52. And because I replaced it, irrespective of whether I got an ace or whether I did not get an ace, probability of my picking an ace in the second card will also be 4 by 52. If replacement is happening, then whether I pick a ace in the first card or whether I pick a ace in the second card, the probability will be exactly same. But if I do not replace, if I say without replacing, the first card, probability that I will pick a ace in the first card will still be 4 by 52. No problem. There are 52 cards and there are 4 aces. But if I see the first card and I then pick a second card without putting this first card back in, that means without replacing the first card, what happens is, first of all, in the deck there are only 51 cards now, right? There are only 51 cards, so probability has changed because of the first event. And if the first card was an ace, then there are only 3 aces in the second card. So 3 if C1 is ace, card 1 is ace. And probability of C2 would be 4 by 51 if C1 is not an ace. So now probability of the second event is dependent on the probability or the occurrence of the first event. Whether first event happened or not, that will affect the probabilities of the second event. Right? So you can see, if C1 is ace, if the card 1 is ace, then the probability of the second card being ace is going to be 3 by 51. Similarly, if C1 is not an ace, then probability of the second card being an ace is 4 by 51. So when replacement happens, they are independent. When replacement does not happen, then they are dependent. We see, technically we never call any two things as dependent on each other. We'll call them as not independent. Because mathematically you can prove independence, but you cannot prove dependence mathematically. Okay. So technically we should call it as not independent. Why do we not write it as dependent? We'll talk about it later. Okay, we have a whole chapter for that. So now you understand, when we are talking about independence or not independence, it matters whether we can replace the first item or whether we cannot replace the first item after selection. So I'll make up a question. So we are saying, in a deck of 52 cards, 3 cards are selected at random. If find the probability that all 3 are ace, if first is cards were replaced after each selection and the second is cards were not replaced after each selection. So first part, if we say with replacement, that means they are independent. If they are independent, then probability of selection of first card, okay, is going to be, or you can say ace in the first card is going to be same as probability of getting an ace in the second card. It will be same as probability of getting an ace in the third card, and that is going to be 4 by 52. and probability that I got ace in the first card and ace in the second card and ace in the third card will just be probability of ace in the first card into probability of ace in the second card into probability of ace in the third card, because they are independent of each other. Now in our calculator, what you can do is you can use bracket. We'll say 4 upon 52, bracket close, and then for raised to, I will press the raised to box button, x raised to box. You can see this button. So if I press that, it gives me a box in the power. Press 3 equal to okay. Now if I say without replacement, then I have to figure out what would be the probabilities if the first card was ace, what would be the probability if the first card was not ace, and so on. Second card is ace, second card is not ace. So for that we draw a diagram called as tree diagram. So I'll show you how a tree diagram would work. These are all branches. So in the first card, I can get a ace or I can get not a ace. So I will write N for not a ace. In the second selection, I can get an ace or I can get not a ace, and same thing here. In the first selection, I got not a ace, and in the second one, I got an ace. Similarly, for the third selection, again two choices. So in a way, I'm saying in the three cards, I'm getting ace, 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 or I'm getting, I'll write it properly here, ace, 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 or ace, ace, not an ace, ace, not an ace, 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 not, not, ace, ace, not ace, not, and not ace, and then not. These are all the possible combinations that we can get from this question. Selection of three cards and whether we have an ace or not an ace. These are all the possible combinations, or even you can call them as permutations. Right? These are all permutations. Now, how likely is that to happen? So let's say in the first card, the probability that I am going to get an ace is going to be 4 by 52. 4 by 52. In the second one, if I had an ace in the first, and here I will have actually 48 by 52, right? I have 48 not aces out of 52 cards. Now, if in the first card I got an ace, then total number of aces for the second card are now 3. Out of total number of cards, that would be 51. Again, for not an ace, I will have 48 cards out of 51. Similarly, for the third one, if I have an ace in the second one, so ace in the first one, ace in the second one, so I have now only 2 aces. So here I will have 2 by 50. Here I will have 48 by 50. Here I got one ace, one not an ace. So for another ace, I will have 3 by 50. Here I will have 47 by 50. Similarly, here if I had not an ace, so I will have 44 cards for the second chance. Here I will have 47 cards. Here if I got not an ace, then an ace. So 3 by 50 and 47 by 50. Similarly here n and then n, I will have 4 by 50 or 46 by 50. Now all I have to do is multiply the probability of a branch. So if I want ace, 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 I will just multiply these probabilities. So here probability for ace, ace, ace is going to be 4 into 3 into 2 upon 52 into 51 into 50. Similarly, if you want another, branch, let's say if you want a n n, if you want probability of this, you would just multiply these branches. Whatever you want, if you want NAA, then this is the branch that you will multiply. So just choosing the branch to figure out what probabilities do you want and multiply the probabilities. This is good if you have multiple questions. Okay, if you have multiple questions, then this is good. But you can imagine if I had more than 2 choices, if I have 5 choices each time, or if I am doing the same experiment 20 times, I'll have to make such big tables, such big tree diagrams. That is not very much convenient. So we have other ways as well. I'll talk about it tomorrow. So right now, if you want the probability, we have 4 into 3 into 2. And the probability of getting ace, ace and ace, or you can say probability of 3 aces, however you want to write. So you can compare, this probability is higher than this probability. So we'll discuss that tomorrow. Now tomorrow the timing of our class is going to be 3 to 4:30 p.m. Now in future we will not have these Saturday and Sunday this exact timings. We'll discuss the exact timings tomorrow. Okay, so we'll talk about the timings, we'll talk about the days of the lectures and stuff. We'll talk about it tomorrow. Okay, so join with the same link at 3 p.m. Bye.